Okay, so for number 3 in our video project, part A, we have an initial current going to the left and the current is decreasing over time. So initially, this current will create a magnetic field that is out of the page inside this box. Because the current is decreasing over time, this box will induce a magnetic field that is also out of the page to counteract this decreasing out of the page initial magnetic field. So an induced magnetic field out of the page would give us an induced current that is counterclockwise. Okay, so now that we know the direction of the induced current, we can figure out the force. So force is equal to QV cross B. So we know that on our left and right side of the box, because they're both equal distance from the current, these forces will cancel out. So we have to examine the top side of the box and the bottom side of the box. On the top side, the velocity, the direction of the current is to the left. The magnetic field is out of the board, so the force will be upwards. Now for the bottom side of the box, the velocity is to the right. The magnetic field is out of the board, so the force will be downwards. Because the top side of the box is closer to the current than the bottom side of the box, the overall force of the top side will be stronger than the bottom force. So the total net force would be upward. Now for B, we have an increasing current creating a magnetic field inside of the box. So if the current is increasing upward, the magnetic field inside of the box would be into the page. Because it's increasing, to counteract this increase in magnetic field into the page, the box will induce a magnetic field that is out of the page. And due to the induced magnetic field out of the page, it creates an induced current that is counterclockwise. So, going back to the equation, force equals QV cross B, the tops and bottom sides of the box are equal distance from the current, so the forces on the top and bottom will cancel out. So we have to examine the forces on the left side and the right side of the box. So on the left side, the velocity is going downwards. Magnetic field, due to the current, is into the page, so the force will be to the right. On the right side, the direction of the current, i.e. the velocity, is going upwards. The magnetic field is into the page, so the force would be to the left. Now, the distance from the current to the left side of the box is shorter than the distance from the current to the right side of the box. So that means the force on the left side of the box will be stronger than the force on the right side of the box, meaning the overall force would be to the right. Now for C, to figure out the direction of the torque vector, we have to look at the equation torque equals magnetic moment cross the magnetic field. So going back to what we did in B, the current creates a into the page magnetic field. Since it's increasing over time, an induced magnetic field to oppose this change will be created out of the board, inducing a counterclockwise current. So the magnetic moment vector would be out of the board due to the induced magnetic field. The magnetic field would be into the board. Now crossing these two vectors, because they are 180 degrees from each other, we know that crossing those two vectors will give us a torque vector equaling 0.